All right. After each of the data collections for each of the parts of the lab, I'm going to go over what to do with the data so you can fill in the rest of the chart. For the rest of the chart, there's a few columns that you need to look at. There's the actual mechanical advantage column, which is the next blank one, followed by the IMA, or ideal mechanical advantage column, followed by the efficiency. Now, the information earlier in the lab handout will give you the equations you need to calculate those, but just to give you more of a conceptual overview, the actual mechanical advantage is the ratio of the amount of force you had to pull, that's the output force, divided by the input force, which is the weight of the object in newtons. So you have those numbers on there, and you can calculate what that means, or what that value is. The meaning of it is basically how much harder you have to, or how much more force you have to put on the outside to get a certain amount of force on the input side. Then there's the ideal mechanical advantage, which is a ratio of distances. That's the IMA. That's equal to the distance from the input, or the distance from the leverage point to the hanging weight. That's your input distance. The output distance is the distance from your leverage point to the point at which you're pulling. So that ratio in, I should say, the ideal world would be the same as the actual mechanical advantage. And the truth is, the actual mechanical advantage may be a little bit less than the ideal mechanical advantage. That ratio is what the efficiency is. So with that in mind, go ahead and make those calculations, complete that part of the table, and we'll move on to the next part of the experiment, which is the class 2 lever. All right, this is now the class 2 lever. And because of some practical issues, I had to hook it up and screw it into my table here. So this is a meter stick, and what's going to happen is we're going to have the fulcrum point at that end of the meter stick all the way down there. And this is the input force, this is the weight, and then this is the output force. This is the force I have to exert in order to keep the system in equilibrium. And so what we're going to be measuring is how much force I have to exert when it's at different locations along the meter stick, and when the input force is at a couple of locations along the meter stick. That's what the second part of the lab is. The input distance is the distance from the fulcrum point to the weight, and the output distance is the distance from the fulcrum point to the point at which I'm pulling. That's what defines the second class lever. So this is what the data will be for the next couple of measurements. All right. So for the first one, and I will say, I had to reduce this. I made this 150 grams, or 1.5 newtons. In earlier versions of the lab, it was around a little over 5 newtons, which makes actually the weight here that I have to pull to keep it up so heavy that it's very difficult to do that. So I dropped this to 1.5 newtons over here. So for the first part of the lab, it wants us to set this to 1.5 newtons and have the input force at 1 meter, which it is right here, it's at the end of the meter stick. And it wants the output force at 0.2 meters, which is 20 centimeters now. So I'm going to be 20 centimeters from the fulcrum point. So I need to figure out how much force, I need to measure how much force it takes to keep that weight up from here. So fortunately I have my force sensor here, and it's taking a fair bit of force here to keep this up. It's taking, if I can see it, gosh, it looks like 9.5 newtons of force to hold up only 1.5 newtons over there. That's what it looks like, about 9 point, let me see, oh, I take it back. Make sure I'm measuring it correctly. Yeah, 9.5 newtons, I'm going to go with that. So I'm going to write that in the proper place. Right here, I have a whopping 9.5 newtons. Now I'm going to move the output force to 0.5 meter from where it had been. So instead of being 20 centimeters, I'm going to move it to 0.5 meter, which is right here. Put the weight on, measure the force it takes to hold it up. Okay, here it's a little bit more modest. See about 3.8 newtons. Okay, 3.8 newtons. I'm going to write that in. Now it wants me to adjust the points at which I have the output force. So I move my input force to the 0.5 meter as it asks me to. And I'm going to take my output force and measure it at 20 centimeters. So for the class 2 lever here, at 20 centimeters, I'm seeing about 6 newtons. All right, so I'm seeing 6 newtons at 20 centimeters, so I'm going to write that in. For this one here, when the input force is at 0.5 meters, I'm going to keep the input force at 0.5 meters, and have my output force at the same point as my input force. You might guess what it should be. Let's see how close we are. I am seeing an output force of about 2 newtons here. Same location as the input force, 2 newtons. Okay, so I've completed my measurements for the levers, both the first and the second class levers. Do the calculations of the AMA and the IMA in the same fashion as you had earlier. And the other thing I'll say, and your efficiency as well, you may notice a little bit of a different efficiency here. It may be lower in this case. Can you think of any reasons why it's lower in this case? I'll give you a little bit of a clue. In the other case, when you had the class 1 lever, you had the same amount of meter stick on both sides. So the effect of the meter stick canceled out. Here, though, you have a meter stick, and the longer the input force is, the more meter stick it has along with it. So when the input force was all the way over here, not only did it have to hold up, when I was at any point here, not only did I have to hold up the weight here, but I had to hold up the entire meter stick as well. That's being hinged from this point. So there's more and more meter stick that I'm having to account for that I was ignoring earlier. That's going to make my efficiency lower in this case than it had been in the earlier case for the class 1 lever. Little heads up. Okay, so here's the setup. Got the ramp, got the roller cart down there, and I have some mass hanging here. The ramp's at a 30-degree angle. How much mass does it take to get the roller cart to roll up the ramp? The roller cart is a mass of about 500 grams. We'll verify that after. But it's going to take a lot less mass here to get that to roll up. That doesn't seem fair, does it? It's actually because of mechanical advantage. And we'll talk about that. But let's first see if we can get the exact mass. Right now there's a 50-gram hanger, and a 200-gram mass, and a 50-gram mass. So there's 300 grams here, and it's close, but it's not quite. You can see there's tension in the string here, but there's just not quite enough mass to get it up. I'm going to slowly add masses of clay to this hanging mass to see if I can get the mass to be just great enough to pull the cart up. And I have a scale here so I can mass the clay as I'm adding it on. This is about 6 grams. I'm going to see if 6 grams is enough to get the cart to roll up at constant velocity. Not quite. Add a little bit more. Let's see. I know it's close because I've been playing with this a little bit. I'll add another 2 grams. It's another 2, it's actually about 3 grams. So let's see if this is enough to do it. It's going. Seems like it's going at a pretty constant velocity. I'm going to go with that and say that that was the mass that just was able to get this cart to pull up. Within a gram or so, that's about it. All right, so what was the total mass of this? I'll check it on my scale and verify. My scale tells me 309 grams total. So we'll say 309 grams is what it took for a 30-degree angle here. You verify that it's still 30 degrees. It hasn't shifted. Yeah, it's 1 meter tall at the 2 meter mark, 30 degrees. The cart weighs, or has a mass of, let's see what its mass is. $517 grams is the cart. 517 gram cart. 309 gram hanger. Okay, I'm going to add some mass to this cart in the next phase. All right, I made sure to enter the mass of the cart, which is 517 grams, and the input mass, which is 309 grams. This is the mass that I added to the hanger. So I'll have to convert that to newtons, but I'll do that in a few minutes. Now what I'm going to do is I'm going to add 500 grams to the cart, and now we'll see how much mass it takes to pull the cart up the ramp. If you've ever used a ramp, this is why. It takes less force to get the cart up the ramp than the weight of the cart. Isn't that great? All right, so right now we have about 250 newtons on here. I'm going to more than double that and put, or almost double that, and I have 450 newtons there. Still isn't going. I'm going to add another 100. That's 550 newtons. Nothing yet. I'm going to go with 600 newtons here. Still hasn't started. Let's see what's going to happen if I put 650 on. Looks like it's accelerating. So 650 is too much. So it's more than 600, less than 650. I'm going to add pieces of clay until I get it to go. And then I'll weigh the whole thing at the end and see what the actual mass is of the hanging system here to get the thing to move up the ramp at a constant velocity. I'm getting there. It's wanting to go. It's not quite there yet. There it goes. It's pretty constant. I could probably take off a gram or two of clay here and see if it's going to maybe not accelerate. It might have had a small acceleration there. My goal is to basically have it have no acceleration. Still heard a little acceleration. I'll drop a little bit more mass. See if I can just get that threshold where it just makes it up the ramp. Taking clay away. Get below threshold. Okay, I think I just reached the point where it's just having to break a little bit of friction down there. Still taking off more clay here. So I went below the threshold there. I'm working myself back up with a little bit of clay. It's a little bit of give and take. I think the string might get a little bit naturally lubricated as I do this. So the weight that didn't work earlier worked later to get it to move up. I'm putting quite a bit of clay to make up for the mass that I took off. Clay is really handy. Oh, look at that. So close. Boy, it's so close, just at the threshold. I'll go with that. There is the breaking of static friction, which makes it a little bit tricky to find the exact threshold, because the friction may not be identical along the ramp everywhere. But this is pretty close. Seeing 588 grams. I'm going to write that in here. All right. Now we're going to do the same. Oh, this was not for 15 degrees. This is for 30 degrees. Now I'm going to drop the ramp so that it's only 15 degrees rather than 30-degree angle. All right, I'm going to repeat the same experiment, but at a 15-degree angle. And in this case, I actually put the track on my table here. I have a big enough table I could do that. And I'm going to show you both sides of it. I put a ruler up at the beginning and at the end so I can measure the change in height of the cart and the change in height of the hanging mass in both cases. I neglected to do that in the 30-degree case, so I'm going to have to go back and get those measurements for you. But what I'm going to do here is record the initial height of the cart, the final height of the cart, the initial height of the hanging mass, and the final height of the hanging mass, so that you have those numbers and you can use those in the lab. All right, I'm going to start with the cart without any extra mass on it. I'm going to slowly add mass to this. Right now I have 50-gram mass plus the 50-gram hanger. I'm going to add clay to increase the weight of that hanging mass over here. As I add clay to it, let's see what happens. At some point, everything should start to slide. Didn't quite do it there. Add a little bit more mass here, see what happens. So 100 grams is too much, causes an acceleration. So I have to add something less than 100 grams there. Okay, I'm really close to the threshold here. Just add a tiny bit more clay to this, and we'll see if it starts to go. Looks like that's the threshold there, approximately. Add a tiny bit more again. That's pretty good. As you can see, there's a little bit of friction and uncertainty in the cart moving up, but I'm going to go with that. I'm going to mass this. 141 grams is what it took to get the cart to go. Now, let me talk about the distances here. When this is at its highest point, I'm going to say the distances it moves are going to be greater or lesser for this as they are for that, depending on how far I let it drop. So I'm going to let this drop a certain distance. I'm going to say it goes from 0 to, let's say, 40 centimeters. When it goes between 0 and 40 centimeters, I want to find out how far the cart over there goes up. So I'm going to drop this to 40 and try to keep it here. Just to 40. Take off a tiny little mass, hope it stays in equilibrium here. At about 40. All right, and I'm going to see where the cart is here. The cart started at this position here at a height of about 8 centimeters, and it moved up to a height of about 18 centimeters. So I'm going to say that the cart went up 10 centimeters. You didn't really see that. I should see that too. What I did is I measured the distance from where the cart started, which was here, to where it ended when the hanging mass was at a 40 centimeter drop. This was at a 10 centimeter rise. So this went up 10 centimeters when that went down 40. All right, and I'm going to put that in the data. See that? I'll say vertical distance, the cart moved upward 10 centimeters. Vertical distance, the hanging mass dropped 40 centimeters. And it's going to be the same in either case. So I can repeat this for the other one of 15 degrees that I'm going to do in just a minute. And I mentioned that the total load here, or the input force, I should say, is what I weighed this to be. What I said a couple of minutes ago, I said I think 314. Let me check that. Can't remember what I said. You'll remember what I said. You can check the video. It was 143 grams is what I had here, if I recall. Now I'm going to do the same thing, but by adding 500 grams to the cart, and let's see what happens. I'm going to just repeat it without starting and stopping the video. I added mass to the cart. You didn't see that, but I did. I added 500 grams to it. And then I'm going to hang this here. Take off all this clay I added. Put my mass hanger back on. And start adding mass to this. I have the 50 gram hanger. I'm just going to start off with 250 grams. Let's see what happens. Nothing. All right. I'll add a little bit of clay. Seems like it's getting close. Add a little more clay. And a little bit more clay. Yet more. Definitely exceeded it there. Take off some of that clay. That's close to the threshold there. Add a tiny bit more. I bet you it'll be there. so close. There's a slight acceleration. I'll take off a little clay. Just a little bit more, taking off more clay. That looks at about the threshold to me. I'm going to weigh it or mass it. I get 273 grams for this one. Okay, now I'm going to go back and make sure I have the data I need for the 30-degree case. Back at 30 degrees, what I'm going to do is I'm going to measure the change in height from a certain point of the hanging mass here to the ground, from right here to the ground, and I'll measure the corresponding change in height of the cart over there. The cart over there, how much does it change height when this changes by whatever height I'm going to measure right now? So let me show you. Back to this. Make sure you can see me. Okay, it's currently at a height of the meter stick says 9 centimeters here. I'm going to drop it to the floor. Means it's going to drop 91 to, it's going to have a difference of 91 centimeters. It's going to go from 9 centimeters to 100 centimeters. The bottom of the wave. That's a 91 centimeter difference in height. While it did that, I'll show you what happened to the cart. While it did that, the cart went from this height here of 13 centimeters to 59 centimeters. That's a 46 centimeter difference in height. From 13 to 59 is a 46 centimeter difference in height. So I'm going to write that in here because I didn't do that earlier. So the vertical distance here is 46 centimeters. And the vertical distance of the hanging mass, I said, was 93 centimeters. And that was going to be the case for both of them. Now what I want to do is I want to redo the actual weight measurement for the case with just the cart, because I think I let it go a little too fast earlier. So I'm going to add mass. I have to add a little bit of clay now. I think that's close to a constant velocity there. Close enough. Here's what was hanging when I did that. I added some clay to it. And I'm going to weigh that. I'm going to mass it. Scale right here. My scale is showing 310 grams. Earlier I had 309 grams. So I was probably fine. But I'll go 310 grams. If I'd known it was that close, I probably wouldn't have changed it. All right. So we have enough data. Now you can calculate the AMA and the DMA the same way you did earlier. You're going to have to convert these grams to weights and newtons, just like you're going to have to convert the mass of the cart plus the 500 grams into weights and newtons. So cart plus 500 is 1,017. Write that in. Okay, you can convert it to weights and newtons, or you can just use it in grams because the units cancel. You're welcome to do that either way, but at this point you can now calculate the AMA, the IMA, and the efficiency in the same way that you did it in the earlier cases. The moral of this is you can get an object up a ramp by using lighter weights if the ramp is shallow. So if you have a really long ramp, make it shallow enough, you can get a heavy object up the ramp by using not that heavy a weight to pull down on it. So the shallower the ramp is, the easier it is to get an object up the ramp. And this is just numerically calculating it in this lab.